mine was better. Mine, the medium.
I just
Bye, have a good day.
If you tell me to shush one more time, end up getting louder.
You and me have two hats.
I am not evacuating. No. See you later, Mr.
Bye, have a good day.
Two. Try not to hate this day. No way.
I think we got that already. What'd you ask? What? What'd you ask?
And he's off right now, my collar is right here.
Oh, yeah. I better change too, man.
I was like, can I ring the bell? And he's like, no. I'll ring up when the bell rings.
I changed in class. Fuck Jim.
Sorry.
There, that's nice.
Alright, what's my glass? This is I just hold it over.
I should just felt like this all day. Holy God, it's hot. Just to be an asshole.
Like what?
Just chill out like this all day.
You won't.
Probably will.
You won't walk around like that, man.
Huh?
You won't walk around like that, man. Let's do it.
Oh. You feel better, Madison? Yeah. No, you're very smart.
This is kind of impossible, Kyle. Unless you got a belt for me.
Being insane.
I came in really deep. I came in here really deep. I was supposed to run a simulator.
test will be 2-7. Who wants to pass back papers?
I'll do it.
Alright. You can split it with somebody if you want to flip it off. Oh, I'm gonna go over in a second. Eric, shut that door for me, please.
The one that was due today.
2-7.
Huh?
2-7.
Oh, this is the whole one.
I'm a ghost.
Look at our minimum bio. Worksheet 2-7, it's over there.
Thank you, Mike.
Alright, while he's passing this back, let's go to worksheet 2-7. Take this out. Tell me if you have questions on it.
Wait, I have a question.
Yeah.
You gave us like a 95 on this, but we didn't finish.
That's why I got 95.
But like we didn't get to that part.
Which one is that? What did you look
The
for?
one that when you weren't here?
Yeah, Cosmos?
Yeah.
Did everybody have the same? Did everybody get a 95 on the Cosmos video?
No.
Some of you did get 100?
Yeah, I gotta go check on it.
Wait, which one is
Okay,
that?
so.
Why did you get 2012? Because I didn't think we got to 16, 17. So
Alright, any questions on this worksheet? Last call. 2-7. Alright, pass it up.
Yeah, but we did 16.
Not if you got it back, obviously. Don't give it back to me. It has to be right on it.
guys are all spread out.
They'll move back again. See where the bar is? When students sit down, they can't help hitting the bar, and so these questions will move this way. That's probably crazy phenomenon.
Oh, someone's actually smart.
These are a lot of papers.
I told you you could split with somebody.
I really don't mind, but I just split it. I don't even know how you do all these.
I don't know.
Give me a
Magic.
Nah, Baron missed this class sheet and never handed out papers back, and at the end of the year, we had a file like that of all of our classwork.
That's the thing, because after a few days, like, I might make mistakes, and I want people to have stuff right. Not that I ever make mistakes, but
What does TF equal? What's that?
temperature and Fahrenheit.
Okay. And TC is temperature in Celsius?
Yep. I should just start around the temperature when I'm done with them.
Sounds good to me.
There's always that one student that wants every paper down.
I didn't get a grade on this.
Yeah, give it back to me. I'll put something with that.
That's funny how it says no red pens when I wrote my name and everything in blue pen.
All right, let's get started here. So, latent heat. Alright, so heat of fusion and heat of vaporization, sometimes they're called latent heat of fusion and latent heat of vaporization.
I have a question.
Yeah,
So for like this class, should we keep all the old stuff too?
you should. You should keep your worksheets just in case I put the wrong grade in, so you guys
Or all
can
our
show me.
notes? like
Yeah.
the final?
And yeah, to study for the final too.
Okay.
Alright, so let's do heat of fusion first. Let's do a line first. So heat of fusion is the amount of heat needed to turn a solid into a liquid. I'm gonna rush, my writing gets worse. Alright, so we know it takes heat to raise the temperature of something, but it also takes heat to change the state. And you may remember from that lab we did last week, when you start heating up the ice water, if you did it really carefully, it takes a while for the temperature to start going up. Because as you add heat to ice, and its temperature gets to 0 degrees Celsius, the temperature doesn't go up for a while after that. When you're adding heat to ice, the temperature stays the same, but the ice starts to melt. And it takes energy to melt the ice, to change its state from ice at 0 degrees Celsius to water at 0 degrees Celsius. So it takes energy just to change it from one to the other. And then once it's all melted and becomes water, then as you add more heat, the temperature goes up again. And then once you get up to the boiling point, the temperature stays the same for a while until you boil all the water and turn it into steam, and only then can you raise the temperature again. And so, so when you did that graph last week, you should have got something that looked something like this. Around 0 Celsius, give or take, the temperature wouldn't move too much early on. And then once most of the ice melted, you see it start to go up, and then somewhere around 100 Celsius, not always exactly because it could be impurities, you would have saw the temperature level off again. And that's because once it was boiling, you have to add a whole bunch of energy to get the water to boil and steam, and only once it's steamed can you raise the temperature above 100 degrees. Okay, so heat of fusion is the energy needed for it to turn the ice into water or any other solid into a liquid. The equation for that is very simple. Q equals m times hf. M is the mass, and hf for water is, let me make sure I don't screw this up, 334 joules per gram. Something interesting to note here. If you think back to last week, when we talked about specific heat, I'll wait till you guys are ready. We can finish writing. So you think back to last week, when we talked about specific heat of water, it's 4.18, right, joules? So it takes this much energy to raise the temperature by 1 degree, but it takes this much energy to melt 1 gram of ice, right? So it only takes a little bit of energy to raise the temperature, or lower the temperature, you have to take that much energy out, but it takes a lot of energy to melt ice. That's why you can throw a few ice cubes into a glass of water, and it'll take that water all the way down to 0 degrees, because it takes a lot of energy to melt the ice, but it doesn't have to take a lot of energy out of the water to cool it down. And then the same thing's going to be true for heat of vaporization.
Do we have to write the C equals 4.82?
No, you guys know that already. Okay, so heat of vaporization, of course, is going to be liquid to gas, right? Evaporating, vaporization. So this is the amount of energy needed to turn a liquid to a gas. So again, the equation is going to be very similar. It'll be Q equals mass times.
Wait.
What?
Do we have to reuse? Like, or you just messed up? Oh.
Q equals mass times, and this time it's just another constant called heat of vaporization. So this makes sense. The solid to liquid is heat of fusion, and then liquid to gas is heat of vaporization. Evaporate, vaporization, so you can remember that. What's that? It's a V. It was meant to be a V. It's closer to a V now. All right, HV for water, and obviously it would be different for every substance. So for water, it is 2,260 joules per gram. And so again, it's interesting to note this is way more than, for example, specific heat, right? And so you think about it, you put a pot of water on the stove, it only takes about 5 minutes to get that water to boiling, right? Because it only takes a little bit of energy to change the temperature of the water up to 100 degrees Celsius. But then once it's boiling, to turn all that water into steam, you can leave a pot of water on the stove for a half hour and there'll still be water left over. It takes a tremendous amount of energy to boil all that water into steam. So that's why it can boil for so long. This is also what cools your body, right? When you sweat, what happens? The sweat evaporates off of you, and every gram of sweat that evaporates is going to take 2,260 joules of heat away from you. That's why you can cool your body even when it's over, hotter than the temperature of your body. You can still evaporate sweat, and that sweat still takes energy away from you. That much for every gram. All right, let's do a couple problems on this because that's what we're going to need to do. The math is really simple for this stuff using these two equations, but I'll do one or two. I washed my erasers today, so I'm going to use paper towels. Okay, so let's say how much heat is needed to turn 15 grams of ice, of water at 100 degrees Celsius. The temperature is not going to matter in this problem, except for the fact that I want you to know it's already at the boiling point. Because if we had to add more heat to raise it up to the boiling point, then we'd have to calculate that too. And that would be the Q equals MC delta T, which we already did a few days ago. All right, so at 100 degrees to steam, let's say to 15 grams of steam. So 15 grams of water turns into 15 grams of steam at 100 degrees Celsius. So we're not changing the temperature at all. We're just taking water that's at its boiling point and turning it into steam at its boiling point. So mass is 15 grams. We know the temperature, but the temperature doesn't matter. And there's no change in temperature, right? So the other thing that matters is since we're going from a liquid to a gas, we use HV, heat of vaporization. Let's check again. 2,260 joules per gram. And so this is simple. It's just Q equals M times HV. So it's just going to be 15 grams times 2,260 joules per gram. Grams goes away. We can plug that in. And it comes out to
Comes out to 33,900.
33,900 joules. And all the problems today that we're going to do are just like this. And the only thing you really got to understand is which equation to use. So if I give you a problem where I say we're doing water to steam, you use this, right? Evaporating water, vaporization. If I say we're turning ice into water, solid to liquid, you use this. Right? You could even write that down if you want. Liquid to gas. And then this one's for solid to liquid.
Is there any of them that go backwards?
Yeah, of course. And if they go backwards, you would just see the reverse. None of the problems in the worksheet. But if they go backwards, it just means if you're turning steam into water, it's going to give off this much energy, right? If you're turning steam into water, then that means the steam is going to lose 2,260 joules for every gram. And where do you see that in real life? Well, if you put your hand above some steam, right, you open something hot and the steam burns your hand. Why does the steam burn your hand? Because for every gram of water that condenses on your hand of steam, it's giving your hand 2,260 joules, which is why steam can burn you a lot worse than water can. One other place that you see this is slightly off topic, but interesting to me. Does anybody know what a double boiler is? All right.
It's like when it boils here and then it comes over.
I'll show you. Let's imagine that you, for some reason, had a green flame, because I'm out of red markers, and you put a pot on it, right? And you want to heat something up, but this thing is going to burn if it gets too hot, right? Like your stove will get up to, I don't know, a couple hundred Celsius, 200, 300. And let's say you had something like chocolate that burns at a little over 100 Celsius. Well, what you could do is you could put water in this pot, and then you could put a second pot inside of here. And for as long as you're boiling this water, as long as there's water in that pot, it's not going to go above 100 Celsius, right? You keep adding heat, and that heat just boils some of the water, turns it into steam, but the water that's still in here won't go above 100 Celsius. And so they use this when you, when people who do like catering and stuff, they take their little chips of chocolate, and when you want to melt it down to make like a chocolate house or a chocolate rose or whatever, you got to melt it and pour it into a mold. They use a double boiler because it'll never get above that temperature as long as you have water in that pot. So this could be used for temperature controls, and you could do the same thing with other substances at different temperatures. All right, I think I've blabbered long enough. Questions? No? Should I do any more examples, or are we good with the math? Okay. Alrighty. Solomon, I need you to do me a favor. I need you to go to my phone that's hanging from the ceiling there, and I need you to push stop on it. There. Yeah, so usually I record third period, because that's my first quiet class. Also, because first period never goes well.